Welcome to maths class. So today we are going to learn about existence theorem. So what does it state? It states that there exists a basis for each finitely generated vector space. So first of all, we'll get to know about what's basis and what is finitely generated vector space. What is basis? If V is a vector space over the field F and B is any subset of V, then B is said to be basis if first B is linearly independent set, and second, if linear span of B is equal to V, that is B generates V, or you can say B spans V. If both these two conditions are satisfied, then only a subset of vector space is called its basis. And now finitely generated vector space. So vector space V over the field F is called finitely generated vector space if there exists a finite subset S of V such that linear span of S is equal to V, or you can say S generates V. So remember one thing, it should be a finite subset. Coming back to the theorem, let's proceed to prove the theorem. So we are given a finitely generated vector space. Let that vector space be V over the field F, and since it is a finitely generated vector space, so there must exist a finite subset S of V such that linear span of S is equal to V. That means S generates V vector space. So now if we have to check whether S is the basis of the given vector space, then we'll have to satisfy the two conditions which we learned about in the definition of basis. So these were that S should be a linearly independent set, and the second condition, linear span of S should be equal to V, which is true in this case, as we can see. Now we only need to see whether the first condition is true or no. Clearly, if S is linearly independent, then S is a basis of VF, and hence the result. But what if S is linearly dependent? If S is linearly dependent set, then according to the definition of linearly dependent set, there must exist an element in the subset S which must be the linear combination of the other elements of S. So since S is a finite set according to the definition of finitely generated vector space, so let us consider S be equal to V1, V2 and up to Vn. So it is a finite subset of vector space Vf, as there are n number of elements in it. So if now S is linearly dependent, the vector, let us consider Vm, which is present somewhere in the S subset, must be a linear combination of the other elements of S, if S is linearly dependent, of course. So now if Vm is the linear combination of the other elements of the subset S, let us consider Vm be equal to alpha 1 V1 plus alpha 2 V2 plus up to alpha m minus 1 Vm minus 1, the element which is before Vm, and then plus alpha m plus 1 Vm plus 1, the element which is after Vm, and then up to alpha n Vn. So Vm is the linear combination of the rest of the other elements of the subset S. Now let's just write the set in which the element Vm is not present. So it will be V1, V2, to Vm minus 1, Vm plus 1, because Vm we should not write, up to Vn, and let it just be called S1. So this is the set in which Vm element is absent. So moving forward, now let us just take an arbitrary element V belonging to the vector space V. As linear span of S is equal to V, so here V element belonging to vector space V must be linear combination of the elements of S, because S generates V. So since V is the linear combination of the elements of S, let us just consider V is equal to beta 1 V1 plus beta 2 V2 plus up to beta n Vn. Since the subset S also contains the elements Vm minus 1, Vm and Vm plus 1, we can write V is equal to beta 1 V1 plus beta 2 V2 plus up to beta m minus 1 Vm minus 1 plus beta m Vm plus beta m plus 1 Vm plus 1 plus up to beta n Vn. So here is the value of Vm, this. Why not we just put it in here? After substituting the value of Vm, V becomes this, and now let's just solve it further. See, here's a term in V1, and when we will multiply beta m into alpha 1 V1, this will be a term in V1 too. So why not just take V1 common? So V will be equal to beta 1 plus beta m alpha 1 bracket V1, and in the same way beta 2 and then beta m into alpha 2 beta 2, it will become beta 2 plus beta m alpha 2 V2, and continuing the same way it will be here beta m minus 1 plus beta m alpha m minus 1 into Vm minus 1 plus here's this beta m plus 1 plus beta m into alpha m plus 1 into Vm plus 1, and then up to so on da 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 da. Here's beta n plus beta m alpha n into Vn. So now since all the alphas and betas are scalars, all these are also scalars. So clearly it can be seen it can be seen that V is now linear combination of V1, V2 up to Vm minus 1, Vm plus 1 up to Vn, which means V is linear combination of the elements of set S1. Remember set S1? In which Vm was not present. It clearly means that V belongs to linear span of S1. Now we started V as an arbitrary element belonging to vector space and ended up by belonging it to the linear span of S1, so it clearly means that V vector space is subset of linear span of S1. Now since S1 is a set with Vm not present in it, and S is a set with Vm present in it, and rest all the elements are the same in both these sets, so this clearly means that S1 is a subset of S, and by the property of linear span of S1 is a subset of linear span of S. And now if you can again remember that linear span of S is equal to V, which means linear span of S1 is a subset of V. So, but V is a subset of linear span of S1, and we are here again with linear span of S1 subset of V. So these two simply mean that linear span of S1 is equal to V, because this is the only situation when it is possible that when V is a subset of linear span of S1 and linear span of S1 is also a subset of V at the same time. So now this is the same situation. We are again in the same situation. Now LS1 is equal to V if S1 is linearly independent, then S1 is basis of V, because S1 is a linearly independent set as well as linear span of S1 is equal to V. So now again the same question. What if S1 is linearly dependent? Now what if S1 is linearly dependent set? The same point again, there must be an element present in S1 set which must be the linear combination of the other elements of S1. So we will just consider another set S2 with that element not present in S2. So again we can prove S2 basis of vector space V if S2 is linearly independent, and again if S2 is linearly dependent, this whole procedure will get repeating and repeating until we get a singleton set with one non-zero element present in it, and we know that a singleton set with a non-zero element present in it is always a linearly independent set. So this will be the point when our repeating process will end and we'll finally get to know that there exists basis for each finitely generated vector space. So our theorem will be proved. So we cannot just go on and go on because we cannot do in this way. So we just write it, the things that I have told you, and hence the theorem is proved. So thank you for watching. Hope you like it.